This question is titled, What is greediness and what is dynamic programming? A good question to ask yourself is, if there's dynamic programming, is there static programming? Well, there isn't. The whole phraseology, dynamic programming, is, I think, a little bit out of date. It really doesn't line up with how we think about things like dynamic these days. We're often talking about things like dynamic typing versus static typing. So I won't go too deeply into the genesis of this terminology. Instead, I want to share with you what we generally think about when we think about these kinds of problems. When we think about dynamic programming, we're often told that what characterizes a dynamic programming problem is optimal substructure and overlapping subproblems. And between you and me, I have no idea what this means. Yes, optimal substructure means an optimal solution can be constructed from optimal solutions of subproblems. That didn't really help. And overlapping subproblems, not quite sure. These 2 points, despite looking very abstract and very obscure, are actually the key to understanding how to approach a dynamic programming problem. And I want to show you this by first talking about a different class of problems, what are called greedy algorithms. Here, we have one of the canonical greedy algorithms. This is the change counting problem. If I'm given a dollar amount and I'm given certain denominations, $20 bill, $10 bill, $5 bill, $1 bill, 50 cents, 25 cents, dime, nickel, and penny, how can I find how to make change for that person using the fewest number of coins? Well, a simple way that I can do that is I can go in sorted order from the biggest denomination to the smallest denomination and see, can I make change with the 20? And just keep trying that until I can't anymore, and then move on to the next denomination, and so forth and so on. And we can prove without too much difficulty that this will be the optimal solution. In other words, if I want to make change for $17.26, the best way to do it, giving back the customer the fewest number of coins and bills, is to give him a $10 bill, a $5 bill, two $1 bills, a quarter, and a penny. Now, this is a classical greedy algorithm. And greedy algorithms are problems where we can formulate them in a recursive formulation often. We can break them down into smaller problems, but they're missing this one characteristic of the overlapping subproblems. You might notice that this is not a recursive formulation. So you might wonder what this has to do with anything that we're talking about so far. But what you can see is I've actually probably already gone through the steps of the iterative transformation, and this is probably the result of having transformed what originally may have been a recursive formulation into a tighter, more Python-friendly iterative formulation. In fact, I can give you an implementation of this that is a recursive formulation. Here we can see with every recursive formulation, we have a base case. There's no denominations to pick from, and some inductive step. And for that base case, we say, okay, as long as that denomination that we're looking at right now is bigger than the amount, yield the denomination, and then subtract from the amount. When we can no longer take $20 bills, decompose the problem into a smaller problem by taking whatever the amount that we had left is and removing the $20 bill from consideration, only considering the $10 bill, then only considering the $5 bill, and so forth and so on. And so here we can see this change could have been implemented in a recursive formulation, or we may have even started with this formulation and then mechanically transformed it into the iterative formulation. Well, whatever the case may be, if we take a look at this problem, we can see that the problem has certain characteristics. One of the characteristics is, and as we'll see in certain formulations, those characteristics are very clear. We are trying to optimize. We're not just trying to answer this question. There are many ways I can give you change. I can give you coins and bills that come up to $17.26. In fact, I'm sure I can remember at least one time in the last year where I was at a store and the person was just staring at the coin register and trying to figure out how to do that, and they just couldn't decide. Two $5 bills and three $5 bills and two $1 bills, a $10 bill. They just could not decide until their till told them, hey, this is what I want you to give back. Well, there's many possible ways to do this. And what we're trying to look for in this particular problem is an optimization of this. We're trying to find the best possible way. Not a possible way, but the best possible way. Subject to a metric, and that metric is the fewest number of things to have in your pocket, the fewest number of bills and coins to return. Note that we do not need to revisit previous answers. In this formulation, we decide how many $20 bills we want to give you, and then we move on and decide how many $10 bills we want to give you. And then we move on and we decide how many $5 bills we want to give you, and so forth and so on. And there is no step at this problem where we say, I gave you too many $1 bills 3 steps ago. Let me go change what I did 3 steps ago. The solution to this problem marches forward relentlessly. It never revisits a past decision. And this is what we call our greedy property. In our greedy choice property, what we're looking at is some problem that can be decomposed in a very similar form as a divide and conquer, but where we have no dependence on future choices and we have no reconsideration of past choices. We make a choice right here, right now. It doesn't matter what's going to happen next, and we never go back to a previous choice that we made. All we need to know is exactly what we're looking at this point in time. And it turns out that change counting is one of these greedy problems that has this greedy choice property. Now, proving that takes a little bit of a mathematical formulation, and we won't go into that here, so you'll have to take my word at it. But I do want to share with you one formulation for all of these greedy algorithms that I very much like. This formulation is to implement a greedy algorithm as a combination of building blocks from the itertools module. You can think of this kind of greedy selection problem as basically a take while for each item, assuming that you have an infinite number of these items. So this basically says, for every item, assume that you have an infinite possible number of those items and just keep taking them until some predicate tells you to stop, and then take that result and chain it together so you get a nice non-nested result. And the chain isn't even necessary. If we don't use the chain, you can just see you get some kind of nesting here that you'd have to then decompose. Well, what this shows you is we never revisit any previous state. What we may need to do is we may need to have some state that gets updated along the way, and we can see in order to implement that, we use a very basic coroutine here that manages our state. We have some coroutine that just kind of counts up to some particular value and yields a true or a false, telling us whether we can keep going or not. We have the standard pumping formulation where we turn this coroutine into a function of one argument. But largely what we can see here is that greedy property at play. We can answer this question without ever revisiting a previous choice that we made. And that is the core to greediness. Well, if we think about what this really means, consider another way that we could formulate this problem. What if I formulate the problem as follows? What if I said, you know what? I'm going to shuffle denominations in any order. I'm not going to have them sorted. And then I'm going to try and figure out how I want to return this change. And you can see that shuffling order is going to determine which of these particular choices that we get back. If I shuffle them in this particular order, you can see, it's going to consider the $1 bills before it considers the $10 bills, and it's going to give me a bunch of $1 bills. It's not going to go in that particular order. And you can see that part of the assertion of this greedy property is ensuring that the data that we're working with is sorted. Another formulation I could choose for this might be something like this. Instead of looking at the one optimal choice and computing the one optimal choice as we go, what if we computed all of the possible choices? And so here, I'm yielding all the possible ways that I could choose a $1 bill, all the possible ways I could choose a $100 bill, this is a penny, all the possible ways I could choose a $1 bill, all the possible ways I could choose a nickel. And you can see here, these are all ranges from 0 up to the total amount that I might have. And when I do that, then I could filter those down to meaningful candidates. Because here you can see one possible candidate, give them 0 back of everything. And you can see when I sum that up, that's $0. That doesn't make any sense. So I'll skip ahead. And here you can see here's another candidate where I give them 2 $5 bills and 2 50-cent pieces and 34 quarters. And it gives me $20.50. And what you could think is I could just look for the next possible solution where it matches up to $17.26. Except from the time that I showed you this first output to this very moment in time, it's still trying to find one. The problem with trying to solve this problem in that combinatoric approach, look at all the possibilities against all the other possibilities against all the other possibilities, and then filter down to one which matches, and then maximize or minimize over this to find the one which happens to have the fewest number of coins, it is enormously expensive. In fact, I still don't even have one candidate answer for this problem, even after over a minute of talking. And the reason for this is the combinatoric explosion of all the possibilities that I have is so enormous here that it's just almost impossible for me to find a solution in a reasonable amount of time. The reason why that greedy formulation is very useful is the greedy formulation is giving me a very fast and very closed off way to answer this problem. Instead of having to anticipate or having to deal with every single combinatoric possibility, I look at one point in time, I make one choice, and then I move on, reduce the problem, make another choice, move on, reduce a problem, make another choice. And this combinatoric explosion is a very common pattern that we'll see when we try to implement dynamic programming algorithms. When we talk about optimal substructure, what we're really saying is the optimal solution for the problem of some size can be solved by looking at optimal solutions of subproblems. We do not have to look at every possible solution. Instead, we can be somewhat parsimonious, or we can be somewhat conservative about how many of these subproblems we look at. We can take the overall best answer and compose that out of the best answers of smaller problems without having to remember, oh, there were 15 million ways to do this problem, 15 million ways to do this problem. Give me the product of those and then see what gives me the best possible answer. We only have to look at one possible optimal choice for each one of the subproblems. The difficulty is in trying to figure out what those subproblems will be. Well, the other characteristic for dynamic programming, other than optimal substructure, is what they call overlapping subproblems. And the canonical example to show you overlapping subproblems is Fibonacci. Here you can see I'm going to calculate the Fibonacci, the 1000th Fibonacci, using my canonical recursive formulation. And you can see this is incredibly slow. This is ridiculously slow. And the reason that it's so slow is when I compute Fibonacci of 1000, it goes off and it computes Fibonacci of 999 plus Fibonacci of 998. The 998th. And when it computes Fibonacci of 999, it goes off and it computes Fibonacci of 998 plus Fibonacci of 997. And when it's trying to compute this branch here, you can see, oh, this computes Fibonacci of 997 plus Fibonacci of 996, and so forth and so on until I get down to my base case, where somewhere here it's term plus term plus term plus Fibonacci of 1 plus Fibonacci of 0, and on the other side. And what you can think is the splay out here is enormous. For every recursive step, of which I will have one step per value, so 1,000 times I'm going to be splaying out twice. So I'd expect this to take 2 to the 1,000th power number of steps. And critically, I'm recomputing a lot of stuff. I'm computing fib of 997, but between when I computed on this branch here, when I computed on this branch here, the answer doesn't change. It's the same answer, but I'm recomputing it unnecessarily. This is why when we look at these problems where there are significant overlapping subproblems, the problems that we're decomposing towards are being repeated over and over and over. We have common techniques like the cache technique or the tabular technique in order to solve this. And you can see with the introduction of just one tiny piece, just this functools.cache, just the idea that instead of recomputing fib of 996 15 times, or however many times it gets computed, I'll compute it once, store that value, and reuse it, turns this from taking almost an unknown amount of time, more than a minute of time, to answering this problem immediately. Now, of course, this doesn't solve the reason why we wouldn't write this in Python, namely that this is a recursive formulation, and if we try this with too large of a value, we'll get a recursion error. But it at least gives us some insight into where the tabular formulation, or in this case, this memoization formulation, this caching formulation, can help us in cases where we're just recomputing the same thing over and over. If we look at the classes of problems that we have, we may start thinking about dynamic programming by first starting to think about divide and conquer algorithms. Divide and conquer algorithms, we're just decomposing the problem into smaller pieces. Greedy problems, well, we're saying that there's some optimal substructure here. What we're saying is the best overall answer can be constituted from the incremental best overall answers. And in the greedy problem, we even know that we don't have to revisit an answer, or we don't have to go back in time, we don't have to go forward in time. We can just make a choice here and there, and the best choice we can make at one point in time is going to be the best choice overall. And then finally, our dynamic programming problems that have both of these characteristics of optimal substructure and of overlapping subproblems. Let me show you a canonical example of a dynamic programming problem. A very common example that will come up is the single source Bellman-Ford. This is an all shortest paths formulation. Basically what you're doing is you're taking some sort of graph, you're notating some source or some sink node, and you want to find the distance from that source to all possible other locations. So what's the fastest way I can go from A to B, C, D, and E? And you can see here I've modeled this it's actually modeled as a directive graph, even though I don't have arrows on these. And you can see they all have approximately the same weight. And I've actually even added one more shortcut from A directly to D which I'll draw with some very crude ASCII art here. So here I have one little shortcut, one extremely crudely drawn shortcut in my ASCII art. Well, you might say, why do we care about Bellman-Ford? Because you already know about graph algorithms. You already know that, oftentimes we'll go to an A-star or a Dijkstra. And it's absolutely the case that Dijkstra can answer this question for us. Here you can see the answer in the form of what the shortest paths are in terms of the weights, and what the actual, or what the cost of the shortest path is in terms of the weights, and what the actual paths are. But it turns out that Dijkstra does not work if we happen to have negative edge weights. And so if we add a negative edge weight, the Dijkstra algorithm just isn't capable of doing this, because the Dijkstra algorithm makes certain assumptions. But the Bellman-Ford algorithm that we'll look at is capable of answering this question if there's a negative edge weight. What that means is we gain something back if we go on a certain path. And so if we take this path from B, or from C to B in this direction going from right to left, we actually have a negative weight here. We actually can negate some of the weight. Now, what this will actually change here is if we look at the path from A to D, without that negative weight, it's right down this little shortcut edge we've created. But if we add in that negative weight, it's actually cheaper for us to pay the cost to go to C and then to have that negated and then to go from B to D. Because this cost, I believe, is just 1. This cost is negative. This cost is 1. And instead of paying a cost of 1 plus 1 plus 1, a 3 versus 2 going down this shortcut, we actually pay a cost of just 1. So you can see it actually changes the path finding. One of the things about Bellman-Ford is it will allow you to solve this problem in the case of negative edge weights, but it also requires that you don't have what are called negative cycles. If I increase the negative weight here too high, then what I might end up finding myself in a situation is to go from A to C to B to D and then back to A may cost -1. Because remember, this weight is 1. This weight is -2. This weight is, or actually, to go from B to C is a weight of 1, and to go from C to B is -2. So here, this is where I found an exploit in the system. If I just bounce back and forth between B and C, every time I make one transfer from B to C, I negate, or I subtract 1 from my overall cost. So the shortest path is always going to be get to C, and then bounce back and forth an infinite number of times, then you get an infinitely negative path. And so Bellman-Ford will actually blow up in this case and say there's a negative cycle that's detected. Well, here is my implementation of Bellman-Ford. I set up some table where I give the destination node and the distance, the best distance to those destination nodes, and then I go through a sequence of relaxing. So I basically go through each possible node and I say, okay, for each possible node, or actually for each one step for all the possible nodes, and we'll talk about why that is. For each edge, is there a better way to get there? And then I just kind of relax these nodes. I find if there's better paths to get here. And this is our dynamic programming algorithm. We can see that it has optimal substructure and overlapping subproblems, except every time I look at a dynamic programming problem and they show the answer, and they just show the answer like this, I look at it and I say, how on earth was I supposed to get that in the first place if you didn't show me the answer? If you're looking at this code, and you're thinking, how did he get to that code? And how did all of this discussion of dynamic programming actually lead to a particular solution? Well, that's what we're going to cover in just a moment.